Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
The topic for today's lecture is interconnection of three-phase voltages. And in last lecture, we saw that there are two ways to connect three phases, star and delta. And we discussed star connection in last lecture, and in this lecture, we are going to discuss delta connection. Okay, so let us move ahead. Fine. So first, let us see how does it look like. We already know how a delta connection looks like. But here we are going to talk about three-phase signals. In our earlier units, we saw how the delta connection for resistance looked like, right? So this is R, this is Y, and this is B. Okay, R, Y, and B. So this is how it looks like. So basically in delta connection, what we do is we connect the finish terminal of one phase with the start terminal of another phase. Now what is the meaning of this? Suppose we are talking about R phase. Okay, if this represents R phase, then it is R1 and this terminal is R2, or this is the start terminal of R and this is the finish terminal of R, right? Similarly, we have Y phase. So this represents Y phase. So this is Y1 and this is Y2, or this is the finish terminal of Y phase and this is the start terminal of Y phase. So what we are going to do is we are going to connect the finish terminal of one phase with the start terminal of another one. Similarly, B is also connected. Okay. Yes. So this is how it is connected together. Okay. Again, we are going to see balanced delta connected system, right? So all the phase voltages are equal in magnitude, but they have phase difference of 120 degrees. Fine. Now, if you talk about Kirchhoff's voltage law, we know that the sum of all the voltages in a closed loop is zero. Right? We know that. Correct? So sum of all these voltages around a closed mesh is going to be zero. Fine? So what we are going to do is, now we are going to derive the relationship between line voltage and phase voltage. Okay? For this, I will be required to draw a diagram. So I will draw the diagram of delta connection now. So this is how the delta connection looks like. This is the R phase, Y phase, and B phase. Okay. Now this is a balanced system. So all the impedances are equal. So I am representing all the impedances by ZPH. Fine. I will take out the connection. So this is IR, R. Then I have Y phase. The current is IY. Similarly, I have B phase and the current is IB. This is the B phase. Okay, got it? Now see, this is B phase. So here the current goes like this. So this current will be IBR because it is going from B It is starting from B and reaching till R. So this current is IBR. Correct? Yes. Similarly, this IR is coming here and it goes in this direction. Okay? And this current is IRY because it is starting from R and it is ending at Y. Similarly, this current is IYB. Got it? So here this is a node and this node is R. Correct? Please keep this thing in your mind because we are going to require this. We will be actually requiring this knowledge. Fine? Okay. Now, what is the phase voltage? Now, if this is a phase, okay, this is phase voltage. Correct? This is our phase, so this is the phase voltage. But please remember that this is Y point, and if I draw only these two, so what is the line voltage? Line voltage is the voltage between two pairs of terminals. So this is phase voltage and this is line voltage. So what can be the conclusion now? These are the parallel terminals. It means what? That what is the phase voltage in this case? Phase voltage is nothing but the voltage between terminals R and Y. Similarly, it will be the voltage between Y and B, or it will be the voltage between B and R. So what is this voltage? VL. What is this voltage? VL. What is this voltage? VL. So what can be the conclusion drawn from this? In delta connection, the phase voltage and line voltage, they are same. Now this is very important point. Okay. In delta connection, the phase voltage is same as the line voltage. Got it? Okay. Yes. So let us move to the next topic. This is the relation between the line current and the phase current. Okay. Now, how are we going to draw this? I've already told you how to draw this phasor diagram, right? First, we have to take the reference voltage, any one voltage as the reference voltage. Okay. So, what I'm going to do is, I will be taking, say I will take VRN as my reference voltage. Okay. Say this is VRN. Now, not VRN, VRY. Yes. Correct? Now, 180 degree, we will have VYB and VBR. Again, we will assume the load to be inductive. So, we will have the currents which are lagging currents. So, this is VRY and the phase difference is phi. Correct? Similarly, here again we will have current IYB. Again phase difference is phi. This will be lagging. Correct? And then lastly we will have a current IBR with phase difference phi. Right? Now what we are going to do is, earlier we used to extend the voltage phasor, but here we are going to extend the current phasor because now we are talking about the current, right? So here I am going to extend this. Similarly, this voltage current, and similarly this current. right? So this is minus IYB, this is minus IRY, and this current is minus IBR. Correct? Yes. So what is the next step? I want resultant R. I want resultant R. So what is going to be my resultant here now? It will be the resultant of these two. Correct? So this is IR. And again this phase difference is 60 degree. Then I want resultant IB. So here I will have the resultant IB. So this is IB. And again this phase difference is going to be 60 degree. Similarly, I want IY. So here I will have IY. So this is my IY, and this phase difference is 60 degree. Got it? So this is how we are supposed to draw the phasor diagram. Fine. I hope you understood how to draw the phasor diagram. Fine? Okay? Yes. So I shall erase this now. Now you know how to draw the phasor diagram. Correct? Now what I am going to do is, here I am going to draw the node which is required for our calculation. Okay? Remember I told you that this we will be requiring later. Yes. So here comes the need. Now this is the node R. So what all currents did we have? This was IR. This current was IBR. And this current was IRY. Correct? Yes? Okay. Now try to understand that the load is balanced, right? So all phase currents. What is the phase current here? Tell me. The phase currents are IRY, IYB and IBR. They are equal. Okay? They are equal in magnitude and have 120 degree phase shift. Correct? Okay? So I can say that the phase current is equal to IRY, which is equal to IYB and which is equal to IBR. This is important, right? Yes. Now let us talk about the line currents. Okay? Now what are the line currents? What is the line current? Line current is IR. This is nothing but line currents. Fine? Okay? Yes. So now we are going to derive the equation. I hope that this is clear to you. Fine? Yes. So after identifying what is the line current, what is the phase current, now we are going to apply KVL at point R. So apply KCL, sorry. Apply KCL at R. Now what is the KCL equation here? We will get IR, what is KCL? Sum of incoming current is equal to sum of outgoing current, right? So IR incoming, IBR incoming, and IRY is outgoing, correct? Equation number 1. Now what I am going to do is, I am going to change slightly the magnitude. Okay, what I am going to do is, because I want IR, so I will convert this equation in terms of IR. So what will be IR? It will be IRY minus IBR. Correct? Equation number 2. Similarly, apply KCL at now Y. Now we can write that equation now. What will be that equation? It will be IY plus IRY, which is equal to IYB. I will convert this equation in terms of IY, which becomes equal to IYB minus IRY. So this becomes my equation number 3. Correct? I shall erase this. Again, I will apply KCL at point B. What will be the equation? IB is equal to, rather I will write the first equation and then we will go to the second equation. IB plus IYB equal to IBR. So IB will be IBR minus IYB. This is equation number 4. Fine? Okay. Now again this resultant can be found out. This resultant can be found out with the help of parallelogram. Okay. So what we are going to do is apply parallelogram. Fine. And the phase difference is 60 degree. I told you that this phase difference is 60 degree, right? So now we will use the law of parallelogram. So by using that law, I can write, we have done that in star connection, okay? So IR square becomes IRY square plus IBR square plus twice cos of angle between IRY and minus IBR. Right? Now what is this angle? This angle is 60 degrees. So what is going to be the next step? We will put that here. Secondly, we know that IRY is equal to IBR, and this is nothing but phase current, isn't it? In the beginning we wrote this equation. So therefore, let this be equation 5. Now equation 5 becomes IR square is equal to phase current square plus phase current square plus 2 phase current multiplied by phase current cos 60. What is the value of cos 60? Half. Correct? So in the next step, we will put the value of cos 60. We will write half. So this gets cancelled. Okay. So the next equation would be, now this after getting multiplied becomes IPH square. This was equal to IR square. Fine. Okay. So what is going to be the next equation? IR square is equal to 3 IPH square. Now what is IR here? IR is nothing but line current. Remember, again we wrote that in the beginning. So therefore IL square becomes equal to 3 PH square, and by taking the square root at both the sides, the line current becomes root 3 times phase current. Now this is very important equation. So what is the conclusion? In delta connection, the line current is root 3 times phase current. But remember, here line voltage is same as phase voltage in delta connection. Now this relation is opposite if you compare the star connection. Fine? Okay? So this is clear? Yes. So let us talk about now power. Before going to power triangle, let us calculate power. So what is going to be the power? Power will be the phase current and phase voltage product multiplied by the cos factor. But this is a three-phase supply, so the total power will be thrice. Correct? So what we are going to do is, we will put these values. Again, this is important, but if we want to calculate the power with respect to line voltage and line current, in delta connection phase voltage is same as line voltage, but phase current is not same as line current, isn't it? So we will put this value into cos phi. So this root 3 gets cancelled by this root 3 here, right? So my power equation becomes root 3 times VL IL cos phi. This equation is important. Now here what is phi? Here what is phi? It is the angle between phase voltage and phase current, not line voltage and line current. Okay, this is also important. Fine? Okay. So this was about power. Now let us calculate the reactive power. Fine. Now what is going to be the reactive power? Reactive power will be, again it will be same thing. It will be same thing, but just instead of cos phi we will have sin phi, right? Otherwise it is the same. Sin phi. And if I wish to change this in terms of line voltage and line current, it would be sin phi. Remember, power is measured, P is measured in watts, and this is measured in VAR, volts ampere reactive, or kVAR. kVAR. Correct? Now if you talk about the total load, now let us talk about the total power, total power, S. It is the total power. Fine. So it will be thrice the apparent power. Per phase. So what is the apparent power per phase? VPH, IPH. Right? Or it is root 3 VL IL. So these are the two equations of the total power in terms of the phase voltage, phase current, and line voltage, line current. Now if I wish to draw the phasor for this reactive power, active power and total power, then my P will be horizontal component, √3 VL IL cos phi. Correct? This is P. My Q will be the vertical component, so this is Q VL √3 VL IL sin phi. And what will be the resultant? Resultant is going to be S, which is equal to, yes, which is equal to square root P square plus Q square, and we have already written this. And if you square root this, you know that you will get sin square phi plus cos square phi. And what is the value of sin square phi plus cos square phi? It is 1. Fine. I hope you understood the power relation in three phase. Okay. Now let us conclude today's lecture. So what did we learn? In fact, I would be concluding the star and delta connection together. Okay. So we saw that the windings can be connected in two fashions, star connection and delta connection. Then in star connection, line current and phase currents are same, but line voltage and phase voltage are not same. So they share this relation that the line voltage is √3 times the phase voltage. Whereas in delta connection, line voltage is same as phase voltage, but line current is √3 times phase current. Right? Secondly, we saw that in star connection, line voltage leads the respective phase voltage by 30 degree, and in delta connection, again line current lags behind the respective phase current by 30 degrees. Okay? Please remember these points because these values will be required at the time of numericals. So with this, we end today's lecture. Thank you so much.